One important and useful property of light is that it can be polarized. To visualize polarization, imagine the waves traveling through a rope. If we move our hand in the vertical direction, the waves will propagate in the vertical plane. We could place a vertical slit in front of the wave and it would pass right through. If we move our hand to side in a horizontal motion, the waves will oscillate along the horizontal plane. We could place our vertical slit in front of this wave, but it would not be able to travel through the slit. If a horizontal slit were used, the wave in the horizontal plane would pass through, but the wave in the vertical plane would not. The wave oscillating in a specific plane is said to be plane polarized. It is important to note that all transverse waves, including light, are capable of undergoing this polarization. It does not, however, state that light is emitted from some source in an unpolarized form. This just means that the electric fields are oscillating in all different planes at once. Since light is made up of oscillating electric fields and magnetic fields, this is also true for the magnetic fields that make up the light, but we really only need to concentrate on the electric fields at this point. Light becomes polarized through a process known as polarization. One way to obtain polarized light from an unpolarized source is to use what is called a Polaroid sheet. This is essentially a series of long, complex molecules arranged parallel to one another so that they act like a series of parallel slits. These slits are known as the transmission axis and allow only one orientation of polarization to pass through. Any light that is traveling in a different orientation is absorbed by the Polaroid. So any light coming out of the other side of the Polaroid sheet is oscillating in the same plane and therefore polarized. The Polaroid sheet that produces plane polarized light is called a polarizer, and the transmission axis can be oriented in any direction. Now when we look at unpolarized light, it has equal intensities in all vertical and horizontal components. After passing through a polarizer, one of these components is completely eliminated. This reduces the light intensity by half. Because half of the light is eliminated, we can say that the resulting intensity, represented by capital I, is equal to half of the original intensity. This holds true no matter what orientation our polarizer is in. A Polaroid can also be used as an analyzer to determine if a light is polarized, and also the plane of polarization. An analyzer is simply a second Polaroid that is lined up with the first. If the two Polaroids are lined up so the slits are in the same direction, you will not notice any difference because the light that was polarized by the first Polaroid is oscillating in the same plane as the slits in the analyzer. However, if you rotate the analyzer a quarter turn so that the slits are now perpendicular to the slits in the first Polaroid, the light will be completely absorbed. This is because the unpolarized light coming into the polarizer is made plane polarized. The second Polaroid, the analyzer, eliminates this light since its transmission axis is perpendicular to the first. Obviously, not every analyzer Polaroid will be exactly at 0 or 90-degree angle to the original polarizer. Sometimes the slits of the analyzer will be at some angle in between. The amount of light that makes it through depends on the vertical component of the angle at which the second polarizer is tilted. This makes sense if you go back to the second polarizer oriented parallel or perpendicular to the first. If the second polarizer is oriented parallel to the first, the slits make a 0-degree angle to each other and no additional light is absorbed by the second polarizer. If the second polarizer is oriented perpendicular to the first, the angle of the slits form a 90-degree angle and no light passes through the second polarizer. A 0-degree angle has no y component, while a 90-degree angle has no x component. So as the y component increases, the more completely the electric field must be being blocked out. That gives us a way to express the amount of light coming through as a function of the y component, or the cosine of the angle. So the electric field that makes it through the second polarizer is equal to the electric field coming in times the cosine of the angle. Since the intensity of light is proportional to the square of the electric field, we can also write this expression in terms of the intensity of light. This is the intensity of a plane polarized beam transmitted by a polarizer at some angle theta to the polarization of incoming light. In other words, this tells us how light that is already polarized is affected by a second polarizer. So how would we describe the orientation and intensity of the transmitted light if unpolarized light passes through two Polaroids? The axis of the first is vertical, and the axis of the second is at 60 degrees to the vertical. The first Polaroid will absorb half of the original light coming in, and the remaining light will come out plane polarized vertically. When that light passes through the second polarizer, the intensity is further reduced by the squared cosine of the angle, which is 60 degrees. The cosine of 60 degrees is 1/2, so 1/2 squared is 1/4. This means that the intensity of the light coming out of the first Polaroid is 1/2 of the original. Multiply that by 1/4, and you end up with the intensity of light coming out of the second polarizer as 1/8 of the original. Okay, so what angle is needed to reduce the intensity of light by 90 degrees? What we're really looking at here is a final intensity that is 10% of that of the original. So we can write an expression that represents that. Then look at our angle equation and plug in what we know. We see the initial intensity on both sides, so we can cancel those out, and we are left with the squared cosine of our angle equal to 0.1. If we square root both sides, we find that the cosine of the angle is equal to 0.3162. From here, all we have to do is take the inverse of the cosine, and we find that an angle of 71.6 degrees will block out 90% of the light. Note that in this case, we are only 18.4 degrees away from completely blocking out the light. So conversely, if you only wanted to block out 10% of the light, you would need to orient your second polarizer at 18.4 degrees. Just a little bit of lovely symmetry.